Good evening, students. Good evening, students. Welcome to MEDIZ Prime. Good evening, students. So myself, Naresh Reddy. Welcome to MEDIZ Prime. And I'm associated with MEDIZ from last 10 years. And this course here is the GTQ series here, GATE 2 questions. So today I'm going to take some probable questions, some important questions, okay, expected in the coming GATE examination from the subject communication systems. And for EC students, as you know, communication systems is the main core subject. Okay, so almost highest number of weightage, highest number of questions can expect from this subject, communication systems. So I hope you already prepared, okay, well for coming GATE examination for the subject communication systems. So I hope you already, and this series, this course which I'm going to take now, I hope it will be useful to you coming GATE examination for the subject communication to attempt the questions in the examination. Means as I said, I'm going to take some important questions here, important questions from the subject communication systems. Okay, so if you see the first question here, I think this is visible to you. The font size is visible to you, I think. Okay, so this first question, if you see, yes, a message signal whose amplitude is uniformly distributed in the range -5, is applied to the quantizer. Input-output characteristics of the quantizer given here is input-output characteristics given here. Range -5 means here x is the input and y is the output. X is the input of the quantizer and y is the output of the quantizer. What you can understand from this quantizer characteristics is, if the input x takes the values greater than 0, then output of the quantizer will be 2. And if the input of the quantizer x takes negative values, then output of the quantizer will be -3. Means if the input values are positive, then those samples will be quantized to 2 volts here, and if the input samples are negative, then those samples will be quantized to -3 volts. So this is the specifications of the quantizer given here. Now we have to find the signal to quantization noise power ratio will be how many dB we have to find. Okay, and this is MCQ question, multiple choice questions, multiple choice question this is. So here one of the option is going to be correct here, and we have to pick that. So here, yes, if the message signal having, it is uniformly distributed in the range -5 to 5. And meanwhile, you can attempt, you can try this question and you can put your answers in the chat box, and I will be in touch with you guys through chat box. Okay. Here I can see some messages. The voice is not clear. Voice is echo. Is the problem still there? The voice echo problem still there? Is the voice is clear? Students, I'm waiting for your response. Is it clear? Yes, I hope it is clear. No? Okay, fine. Yes. Now I think the voice is clear. Now I think I can proceed further. I can proceed further now. Yeah. Yeah, good evening everyone. Good evening everyone. Okay. Yes, fine. Now here the message signal, it is uniformly distributed in the range -5 to 5. Okay, so here the density function of the signal given, density function of the signal given means the input signal we can understand as a random signal. So here the message signal here, what you see, the message signal here is a random signal we can understand. Okay, so which is having uniform density function in the interval -5 to 5. So the input I'm taking is a random signal. I'm denoting with some x. Okay, and if you see the density function of x here, yes, fx of x with respect to x, the density function of x will be like this, -5 and 5. Okay, Uniform density function means the density function is constant. Then what the height will be? The height of course will be 1 by 10. Okay, so the input is a random signal. I'm denoting with some capital X here, and this is the density function of the random signal. Now, this random signal is given as the input to quantizer. This random signal X is given as the input to a quantizer. Okay. Now, in this quantization process, we have to find signal power to quantization noise power ratio. We have to find out. So first, if you see the signal power S, I'm denoting with. So it is nothing but power of. It is power of X only. This is here. This random signal X is getting quantized. Okay. So here signal power is nothing but power of X only. How to find the power of a random signal? That is expectation of X square. The mean square value will give you power. Okay, the mean square value of X will give you power of X. Okay, how to find mean square value of X is expectation of X square. And if you try this expectation of X square, this is integration. For which quantity you are finding expectation? Same quantity, X square, multiplied with the density function of that random variable, fx of x dx, where x takes the values from where to where? Minus 5 to 5. Okay. So in plotting the density function, a small x specifies the values possible for random signal. Okay, the values possible for random signal will be from minus 5 to 5. Okay, now, and if you substitute the values here, this is integration minus 5 to 5 x square. Fx of x is 1 by 10 dx. Okay, now it will be, so 1 by 10 I'm writing outside. And integration of x square is x cubed by 3. This is, and the limits will be minus 5 to 5. Okay, now, so if you substitute the limits here, then you will come to know this is 1 by 30. This is, so 5 cube means this is 125 plus 125. This is, so this is 250 by 30. This is, so is this is what you are going to get, 250 by 30. This is, so this is, yes, in the range minus 5 to 5 and 1 by 10, and x square fx of x dx, x cubed by 3. This is, okay, and 25, 5 is 125. Okay, 250 by 30. And if you do this, you come to know this will be how much? The signal power, okay, it should be 100 by 12 you have to get. Yes, no, this is, it should be 100 by 12. Expectation of x square fx of x dx, fx of x is 1 by 10, okay, and x square x cubed by 3. This is, okay, 5 cube minus 5 cube. This is 125, 30. So it should be actually, this is 100 by 12. This is, let me check like this also. So what is the signal power you got? Yes, yes. Yes. Let me check with Calci how much this is going to be. This is, yes. Yeah, this is 8.333 you will get. Okay, this is signal power what you got. Yes, yes. 25 by 3 signal power. Yes, fine. So most of you given correct answers already. I got the answers in the chat box. Okay, 5.52 is the answer given by the students. So let's check the validity of that. Let's check whether that is going to be correct or not. Okay, now let's find out NQ, quantization noise power. This is quantization noise power. Quantization noise power is nothing but the power of this is QE variable, this is. Okay, QE here is the quantization error, or this is also called as quantization noise. So we have to find the power of quantization noise, we have to find out. Okay, now this is, so power in expectation of this is QE square. QE is a error variable. Error variable means it is a random variable. How to find the power of a random variable? That is expectation of QE square. The mean square value will give its power. And where QE is equals to quantization error. Quantization error is, this is the sampled voltage minus quantization voltage. Will give you the quantization error. Okay. So here the sampled voltage, here X is going to be quantized, and the resultant quantization voltage I am taking XQ. Okay, the X is getting quantized to some XQ I am taking. So here the quantization error is X minus XQ. So this will be now expectation of X minus XQ square, this is. And if you find this, this will be integration. For which quantity we find expectation? The same quantity, that is X minus XQ square, multiplied with the density function of the random variable fx of x dx. Okay, where x takes the values from -5 to 5. Okay, now if you observe the specifications of quantizer, when x takes positive values, okay, then those positive samples quantize it to 2 volts, and when x takes negative values, those samples will be quantized to -3. Okay, so here, so if you substitute that, yes, so this is fx of x is 1 by 10, I'm writing outside, and when x takes negative values, okay, then xq, okay, the x is getting quantized to what? When x takes negative values, that is getting quantized to -3. So xq is -3, so minus minus, that will be plus. So x plus 3 whole square dx, okay, plus. And when x takes positive values 0 to 5, okay, then when x takes positive values is getting quantized to 2 volts, that is given as the specifications of quantizer, then xq will be 2. So x minus 2 whole square dx, this is. So if you do the integration and substitute the limits here, 1 by 10, this is, so it is x plus 3q by 3. Okay, the limits will be -5 to 0 plus x minus 2q by 3. The limits will be 0 to 5. Okay, I already done this computation. Okay, you just check this. Okay, this is, you will get 7 by 3 you will get. Just check from your end. Okay, you have to get 7 by 3. So it is NQ. Then if you try to find out S by NQ, signal power to quantization noise power ratio. Signal power we got 25 by 3 we got signal power, and quantization noise power is 7 by 3. Then S by NQ, if you do, you will get 3.57, you will get 3.57. But he is expecting S by NQ in dB. So in dB is equals to, the power ratio in dB is, that is 10 log. So 10 log S by NQ, 10 log 3.57. So you will get, this is 5.52 dB you will get. 5.52 dB. So which option is correct here is option A will be correct. Yes, option A will be correct. This is, let me check the chart box once. Yeah, 5.52. Yeah, Tushar, you are correct. Sanil Yadav, I studied from you in 2015. Oh, good, Sanil. After a long time. Yeah, Tushar, sir, it's B equals to B minus A square by 12 as variance of uniform random variable. Yes, that's true. You can do quantization signal power like this also. Mr. Tushar is saying like, so if you see, The signal power, yeah. So if you see the signal power, that is expectation of x square. You can find signal power in other way also. How you can find is, so it is the total power of this random variable x only, mean square value means. Total power means you can write as dc power plus ac power you can write, where mx is the mean will give you dc value, the square of dc value will give you dc power, and variance will give you ac power, then that will give you the total power. Now here the density function, here what you see, the density function of x is given, it is symmetrical about this r is in here, then the mean will be equal to symmetrical point. If the density function is symmetrical, okay, about r is in here, okay, then the mean will be equal to that symmetrical point. So mx, the mean will be 0, the variance will be equals to. If the density function is uniform density function, the variance simply you can write length square by 12 you can write. So it is, what is the length here? The length is 10 here, the total length is 10. So that length square by 12. Yes, for uniform density function, the variance is, okay, length square by 12. So length is 10, so 10 square by 12. So yes, you will get, this is 25 by 3 you will get. You can do like this also. Okay, let's move to the next question. Okay. So let me read this question. Okay, so I will see who will give the answer first in the chat box. So I want to check that. Shubham, I also studied from you. Nice to hear you again. Yeah, Shubham, nice to see you. From my side also, I'm happy to see you. So I'm getting opportunity to to get connected with the old students here. Okay, I'm taking this opportunity here. Yeah, fine. Yes. Yes, if you see this question, for a binary digital communication system, the signal component out of the correlator receiver, okay, the signal component out of the correlator receiver. So this question is about correlator receiver, okay, and it is a binary digital communication system. So it is a digital communication system, and it's about correlator receiver. So it is clearly given the signal component. The signal component out of the correlator receiver is denoting with AIT, the signal component. Okay, that can be plus 2 or minus 2 volts, okay, with equal probability. Okay, and if the Gaussian noise at the correlator output has variance of 4, the Gaussian noise at the output of correlator having the variance of 4. The probability of bit error we have to find out, means probability of error only, this is nothing but we have to find probability error. So students, this question is about finding probability error of the digital communication system and which modulation scheme used, the data is not given here. So directly the output of correlator receiver directly given to us. So if you know the data about what the output of correlator receiver, what the signal components at the output of correlator receiver, what will be the noise component at the output of correlator receiver, yes, you can find probability of error directly, you can find out. So how you can find out is, yes, if you take a correlator based receiver, this is correlator receiver, okay, the output of correlator receiver, yes, we sample here. Okay, if the bit duration is capital T, if at all bit duration is capital T, then we sample it capital T here. Okay, then whatever the output we get here, that output if you denote with some y here, okay, so this is signal component plus noise component you will get. The signal component I'm denoting with AIT, and the noise component I'm denoting with some N, and this is given to threshold detector. Threshold detector, and here some threshold voltage will be there, I'm denoting with some V threshold. Okay, now if you see the correlator receiver, it is actually multiplier followed by integrator, so I'm not going to the details because the output of correlator receiver directly given to us, okay. Now so here this threshold detector will make the decisions in favor of 1 and 0 based on this Y value. Okay, this input of a threshold detector, the observation what you see y here, it is the combination of signal component and noise component. And in the question, the data related to signal component and noise component is given. Okay. And if y greater than v threshold, that is coded as 1, and if y less than v threshold, then decision will be taken in favor of 0. That is what you see in a binary system. Fine. So if you know the observation, the input of threshold comparator, if you know, then to find the probability of error, directly you can use this formula, q of a1 minus a2 by 2 sigma n. This formula can be used. When this formula when you can use this formula is if you know the observation, I mean to say if you know the input of threshold detector, then yes, this formula can be used to find probability of error, q of a1 minus a2 by 2 sigma n. Okay. So here, yes. So here a1, a2 here, the signal components only is what you can understand. Okay. So a1 is the signal component when 1 transmitted, and a2 is the signal component when 0 transmitted. Okay. Now here I can understand that okay, the signal component when 1 transmitted is 2 here, and the signal component when 0 transmitted is minus 2, is what I can understand from the given data. So a1 is 2 and a2 is minus 2 here. Okay, this a1 is 2, a2 is minus 2. This is okay. Actually speaking, this a1, a2 will be the mean of this y. Actually speaking, that is the mean of this observation when 1 transmitted. The mean of y when 1 transmitted is a1. The mean of y when 0 transmitted is a2 actually. Okay. But here the mean of y, it is simply the expectation of y will be simply expectation of AIT only, because the noise here is given as Gaussian noise. So for Gaussian noise, the default mean will be 0 only. The expectation of this n, the expectation of noise variable by default will be 0 only. So here the expectation of y is same as expectation of AIT. Okay. So here the signal component, what you see, it's a constant here, 2 or minus 2. Expectation of constant is same constant only, will be same constant. Okay. So that's what. So simply what you can understand here is the a1 here. Okay, in this formula. Okay, what you can understand is a1 is the signal component when binary 1 transmitted. A2 you can understand the signal component when binary 0 transmitted. And sigma n square, okay, it is actually the variance of this observation y, but the variance of this observation y is same as variance of noise variable, because variance will give you AC power, and the signal component what you see, it is just some DC, can be 2, can be minus 2. The variance of DC will be 0. The variance of y is same as variance of noise variable. So variance of noise variable, you can directly take as, actually it is variance of this observation y, but you can take that as variance of noise variable only. And what that is given, variance of noise variable. Okay, the Gaussian noise at the correlator output has variance of 4. Okay, so here the sigma n square is given 4. Then sigma n will be equals to 2. Okay, because I need sigma n here. So by substitution, you will get q of a1 minus a2. a1 minus a2 means 2 plus 2 by 2. Sigma n is 2. Okay, so this is q of 4 by 4. Okay, it is q of 1. Yes, if you check the options are given in terms of q function only. So q1, so which option here correct is q1, option B will be correct here. Option B will be correct. So let me check how many of you given correct answers. Yes, yes. Q1. Most of you given, almost everyone given correct answers only. Very good. Harsh, Ajay, Samskar, Pawan, Ankita, Ajay, Kusum, Ashwin, Kush Kumar. Yeah, everyone given correct answers only. Very good. Yeah, Shivam, Devansh, Vidya. So good. Very good. So let's see the next question. Just look at this question once. I will check the chat box. Just go through that question. Okay. Yes. Yes, if you see this question here, a Gaussian voltage random variable x has 0 mean and variance 16. Okay, so here this x here is a Gaussian random variable, I can understand. Okay, has 0 mean, so expectation of x is 0 and variance is 16 and sigma x square is given 16. Okay, so this voltage x is applied to a square device with a transfer characteristics y is equals 10x square. The mean value of the output voltage y we have to find out. Okay, so this random signal x is given to a square device, okay, where the output y is given by, that is 10x square. Okay, this y is equals to 10x square. Now we have to find the mean value of the output voltage y, means we have to find expectation of y, we have to find out. Okay, so this is numerical answer type question, so no options here. So this is the fill in the blanks type question. So give me the answer, let me check. So very good, a very fast response from you guys, I'm very happy with this. Okay, 160, very good, very good. So it will be 160. Yes, see this. So it is a simple question. Okay, so in GATE examination, the concept based question you can expect. Don't think the questions will be very lengthy. Some questions will be, but very, I mean to say, less probability will be there to expect questions which are very lengthy. Okay, so 1 or 2 questions you can expect. Okay. So from subject communication systems, but most of the questions are concept based questions only you can expect. Okay, like if you see here, expectation of y is equals to, so it is expectation of 10x square, this is 10x square. So 10 is just a constant I can add outside, 10 into expectation of x square. Okay, this is expectation of x square. Expectation of x square means it is mean square value of x here, mean square value of x. This mean square value of x you can write as, okay, mx square plus sigma x square you can write. Expectation of x square means it is the total power of x only, this is. You can write this as a DC power plus AC power, you can write mx square plus sigma x square. Mx is nothing but expectation of x only. Expectation of x given how much? 0 is given, this is. And sigma x square is given 16. So it will be 160. Okay, so 160 will be the answer. The variance of, okay, x is given 16, so by substituting that, okay, then you will get expectation of y will be 160. So 160 will be the answer. So this is a very simple question. Okay, now if you see this question, try this question. Yeah, thank you Natasha, thank you Ajay Singh. Yes. Now what about this question? This is also numerical answer type question, fill in the blanks type question. I think Shruti Goyal, Shivam Gupta, I think you are my recent students only. I think I come across these names. I think you are my classroom students, I think. Yes. For current session students only, I think some students I can see the names, I can recognize the names. Yes, fine. Now, so let me increase the font size for the sake of some students. Yeah. So here, you consider the signal S of t is equals 20 phi t, where phi t is an orthonormal basis function. Okay, this phi t is an orthonormal basis function. The signal is passed through an AWGN channel and received by a filter matched to phi t. Okay. Now, the maximum peak amplitude at filter output will be dash volts. We have to find out. So this question is about matched filter. Okay, but it is a little tricky. Okay, so how this becomes tricky for us is, so here the signal ST, it is given as 20 phi t, where phi t is the orthonormal basis function. Okay, now this is passed through AWGN channel and received by a filter matched to phi t. So this is received by the filter, that filter, yes, we call as matched filter. Okay, and this is matched to phi t. Matched to phi t, this matched filter is matched to phi t means whose impulse response phi t, whose impulse response h of t is equals to phi of, okay, this is tb minus t, where tb is the bit duration, the duration of s of t. Okay, so if the duration of s of t is some tb, okay, then the impulse response h of t matched to phi t, matched to phi t is nothing but the impulse response ht is phi of tb minus t. Okay, now then what is the maximum peak amplitude at filter output? We have to find out what is the maximum peak amplitude at filter output. So here, so those who attended my classroom session, I think they can easily solve this question. So this is maximum peak amplitude at matched filter output will be equals to, this is under root of EB. This is under root of EB. Yes, yes students, if the matched filter matched to orthonormal basis function, instead of matching to the incoming signal itself, instead of matching to ST, instead of matching to incoming signal ST, if at all it is matching to orthonormal basis function phi of t. So in that case, the maximum peak amplitude at the output of matched filter will be equals under root of EB, where EB here is, energy of this ST. EB, energy per bit. Okay, the energy of the incoming signal, energy of S of t. So if you see the energy of S of t, it is integration s square t dt minus infinite to infinite, and if you substitute the respective, okay, this is 20 phi t square dt, this is, and it will be equals to 400 and integration minus phi to minus infinite to phi square t dt. Okay, so integration phi square t dt means it is energy of phi t only, and energy of phi t of course will be equals to 1. Okay, because phi t is the orthonormal basis function. For orthonormal basis function, energy will be equals to 1. So this is 400. This is EB equals to. Then maximum peak amplitude, maximum amplitude at matched filter output is under root of EB, under root of 400. This is 20 volts, I can say. This is 20 volts. So it is a numerical answer type question. The answer will be 20. Okay. And one thing, if at all this matched filter matched to incoming signal itself, if nothing mentioned in the question, if the question is just given that this S of t is given to matched filter, just it is mentioned that given to matched filter, okay, then you have to find what is the maximum peak amplitude at the output of filter. We have to find that. Okay, then what is the default you can understand is
this matched filter is matched to incoming signal itself, that is h of t equals to, this is s of tb minus t. If nothing mentioned, means the matched filter matched to incoming signal or matched to phi t, the data is not given in the question, the data is not given. Okay, just the statement is given that this s of t is given to matched filter, that's it. Then what is the default we have to understand is this matched filter matched to incoming signal itself, So in this case, what is the maximum peak amplitude at the output of matched filter will be equals to EB itself, that is equals to energy of the incoming signal itself. Okay, so this is a tricky question, so take care of this. Okay, so if the matched filter matched to orthonormal basis function, then the maximum peak at the output will be under root of EB, and if the matched filter matched to incoming signal itself, then what is the maximum peak amplitude, AMP I mean to say amplitude, maximum peak amplitude at the output of matched filter will be EB, will be. Okay, yes. Now if you see this question here, so let me little enlarge this. Okay, so go through this question, everyone. It's a good question, this is. Yeah, so some of you given the answer 400 given for the previous question. Okay, so I think you got confused a little. Okay, so that is actually 20. So Mega Agrawal, I think I cleared your doubt. You're saying the maximum peak amplitude is energy of that signal. Okay, yes, it is energy of the signal provided the matched filter is matched to incoming signal itself in that case. But in the question it is clearly given that the matched filter is matched to orthonormal basis function. Okay, so in that case the maximum peak amplitude will be under root of EB, will be equals to. Okay, fine. Now if you see this question here, now statistically independent zero mean stationary random processes xt and yt have autocorrelation functions. So if you observe here, statistically independent, so here xt and yt are independent, you can understand. Okay, xt and yt are independent random processes. Okay, and they are stationary random processes also given, stationary random processes. So xt and yt both are stationary random processes. Simply stationary random processes means triple S random processes only, you can understand. Strict sense stationary random processes means xt and yt के लिए, for these two random processes all statistical parameters are independent of time, is what you can understand. Stationary random processes, and the corresponding autocorrelation functions also given. Autocorrelation function of xt and yt is given. Rx tau is e power minus 2 mod tau, Ry tau is cos 2 pi tau. ACF of xt and yt given to us. Okay, yes. And one more thing given here is xt and yt दोनों के लिए, for these two random processes the mean will be 0. Okay, so 0 means stationary random processes xt and yt. Okay, so xt yt independent, at the same time the mean will be 0, means expectation of xt will be 0 and expectation of yt also 0. 0 mean random processes. xt, for xt the mean will be 0 and for yt also the mean will be 0. Okay, now the random processes w of t and v of t defined as, so he is defining two new random processes here, w of t and v of t, where w of t is xt plus yt and v of t is xt plus yt and v of t is xt minus yt. Okay, so here two new random processes are defined here, W of t and V of t. Now what we have to find out is the cross correlation of W of t and V of t is denoting with RWV of tau. The cross correlation between these two random processes denoted with RWV of tau at tau is equal 0 will be how much? So a cross correlation function का value क्या होगा? At tau is equal 0 we have to find out. It is MCQ type question, so we have to check which option will be correct. So I want to see how many of you will give correct answer for this. So very good, I'm very happy with your answers. Okay, 0, very good. I think 0 will be the correct answer. Yes, so good, so good. Yes, Ajay, Devansh, Sagnik, Shruti, Goyal, Sajita, Shivam, Kusum, Ankita. Yes, everyone given correct answers. So good, so good. Now see this, the cross correlation of W of t and V of t. So this is RWV of tau is equals to, okay, so correlation is nothing but expectation of product. The expectation of product will give you the correlation. Okay, so here between two different random processes here, W of t and V of t. Okay, the correlation between two different random processes will be cross correlation for us. Okay, and the correlation for the same random process at two different time instants will be autocorrelation, and correlation between two different random processes will be cross correlation. Okay, so this is expectation of W of t1 V of t2. This is okay, or you can denote this with like this also, R W V of t1 comma t2. This is, you can denote like this also. Here where tau specifies the time difference here, time difference, t2 minus t1, t2 minus t1. Okay, so here I'm trying for the correlation between these two random processes. Correlation means it is simply the measure of similarity. So what is the degree of correlation? What is the degree of similarity between these two random processes? By observing at the time instants of t1 and t2 you can understand. Where tau specifies the time difference here, t2 minus t1, you can understand as the time difference. Okay, now so you can use this formula also, R expectation of W of t into V of t plus tau. So to find the cross correlation between these two random processes, this formula also can be used. What is the time difference here? I'm finding the correlation between these two random processes with the time difference of t plus tau minus t. T plus tau minus t means tau. So I'm finding the correlation between these two random processes with the time difference of tau. Okay, or you can see like this also. I'm finding correlation between these two random processes with the time difference of t2 minus t1. So t2 minus t1 means tau only, you can understand. Okay, fine. But I'm going to use this formula. Okay, so rather than dealing with t and t plus tau, it's better to deal with t1 and t2 for mathematical convenience. Okay, fine. Now substitute the values here. Yes, expectation of W of t1. Okay, W of t is xt plus yt, no? So W of t1 is, this is xt1 plus yt1. This is okay, into vt2. What is v of t? V of t is xt minus yt. V of t is xt minus yt. So v of t2 will be, this is xt2 minus yt2. This is okay. Now you can do the multiplication and apply expectation to each term. You can apply. Okay, then expectation of, this is xt1 into xt2. Yes, if you do multiplication of these two terms. Okay, next xt1 into yt2. This is minus expectation of xt1 into yt2. okay, plus expectation of, okay. So this is, and if you multiply these two here, this is yt1 xt2. So expectation of this is yt1 xt2, this is. So finally we left with this term yt1 into yt2. Of course this negation sign is there, so this is minus expectation of yt1 into yt2, this is, okay. Now so expectation of xt1 xt2 is, it is nothing but autocorrelation function of xt only. This is same random process xt only at two different time instants t1 and t2. For the same random process means it is autocorrelation function only. So it is, I can write rx of, what is the time difference, t2 minus t1. t2 minus t1 you can write as tau only. This is, you can write rx of t2 minus t1 or rx of tau you can write, okay, minus. It is clearly given in the question xt and yt both are independent, both random processes are independent. Because both are independent, because xt and yt both are independent, we can apply expectation separately to xt terms you have to apply, and separately to yt terms you have to apply. So that point you have to keep in mind, okay. Whenever in the question it is given that independent random variables are independent random processes, then you have to apply expectation separately, you have to apply. That you have to keep in mind, okay. Now plus expectation of yt1 xt2. Here xt yt both are independent given, so you have to apply expectation separately. Expectation of yt1 into expectation of xt2 minus, okay. Now expectation of yt1 yt2, it is autocorrelation function of yt. I can write ry of t2 minus t1 or ry of tau I can write, okay. Now this is the mean of xt only at the time instant t1. It is mean of yt at the time instant t2, but it is clearly given in the question here xt yt both are stationary random processes, okay. It is given in the question both are stationary random processes. Stationary random processes. Stationary random process means the mean is independent of time. Mean square value, variance, all statistical parameters will be independent of time, okay. So here the mean of xt and yt given 0 here, okay, and at the same time both are stationary random processes. So mean of xt is 0 means at every time instant the mean will be 0 only, because that is basically a stationary random process. The mean of xt 0 means what it means is at every of the time instants the mean will be 0 only. So expectation of t1 will be 0 and expectation of yt2 also 0, okay, and expectation of yt1 expectation of xt2 will be 0, because for xt and yt, okay, the mean given 0, fine. So this is rx tau, this is cross correlation between w of t and v of t is rx tau minus ry tau, okay. At tau is equal 0 now we have to find out. So what is the cross correlation between these two random processes? At tau is equal 0 we have to find out. At tau is equal 0, this is rx 0 minus ry 0. Of course at tau is equal 0 is what you can understand. At tau is equal 0. Rx 0 minus ry 0. What is Rx 0? Yes, Rx tau, Ry tau is given in the question. Then Rx 0. Rx 0 is e power 0 is 1 and Ry 0, cos 0 will be 1 only. Rx 0 is 1, Ry 0 also 1 only. So this is, so it is 1 minus 1, so will be 0. This is. So it is MCQ type question. The option C, option A will be correct here. 0 will be correct. Okay. Yes, 0. Fine. Very good. I hope these are those who attended the classroom sessions. There's a very easy discussion only here. What you see here, I think you can easily understand this. Okay. Now, you see the next question here. I think this is visible to you. Is it is visible or I have to expand? Just give me your inputs. So I want to see who will give the correct first answer. So I will read for you. This is consider the memoryless channel shown below. This is okay. Where two inputs here x1, x2 and two outputs here y1, y2. Okay. And this is p y1 by x1. It is mentioned. The channel probability is given here. P y1 by x1. What is the probability of transmitted x1 received as y1? Okay, p y1 by x1. And these probabilities given to us. P x1 is given 0.4. Okay. And p y1 by x1 is given 0.6. P y1 by x2 is given 0.8. Okay. If the optimum detection is used at the receiver end, then the probability of error will be how much? We have to find out. So here you have to give importance to that optimum detection. Optimum detection means you can understand map detection algorithm only is what you can understand. Map detection algorithm means to decode this received symbols. What are the received symbols here? Y1 and y2. To decode this received symbols y1 and y2 at the receiver end, the map detection algorithm is used. Okay. So based on that map detection decisions, what are the decisions you will get from that map detection algorithm? So based on those decisions, you have to find the probability of error. We have to find out. Probability of error you have to find out. Okay. So instead of giving optimum detection, he can give you optimum receiver. Okay, optimum receiver or optimum detection, or you can mention like map detection is used. The question can be framed in any way. Okay. Yes. So first you have to decode the received symbols now. First you have to decode now received symbols with the help of map detection algorithm, map decoding algorithm, and based on the decoding decisions you have to find probability of error. Okay, so important model of question. So 0.36, very good, very good, very good. Most of you given 0.36 only, very good. Now see this, let me do this. Yes, so here the channel diagram is given to us. Yeah, the channel diagram is given. So let me complete this channel diagram now based on the inputs given to us. So I will complete this channel diagram. The inputs are x1, x2. Outputs are y1, y2. Okay. Now p y1 by x1 is given as 0.6. Okay. So here, yes, p y1 by x1 means what is the probability of transmitted x1 received as y1? Transmitted x1 received as y1 is given how much? This is given as 0.6. Okay. So the chances for transmitted x1 received as y1 is 0.6. Then what are the chances for transmitted x1 received as y2? Of course will be 0.4. we can feel like this. If 40% chances are there, if 60% chances are there for x1 to be received as y1, then with remaining 40% chances, the transmitted x1 will be received as y2. Okay, now fine. What else given? P y1 by x2 is 0.8. Transmitted x2 received as y1. Transmitted x2 received as y1. Transmitted x2 received as y1. How much given? This is okay, 0.8. Then what are the chances for x2 received as y2? 0.2. Yes, with 80% chances the x2 is received as y1, then with remaining 20% chances x2 will be received as y2. So this is how we can complete the channel diagram. We can complete. Okay. Now px1 given how much? Px1 is given 0.4. Okay. Then what will be px2? Px2 of course will be 0.6. If 40% chances are there for x1 to be emitted from the source, with the remaining 60% chances x2 will be emitted from the source, we can understand. Okay, now fine. So we have to find probability of error by using optimum detection. We have to find probability of error. Optimum detection means, as I said, map detection we have to use. So first we have to decode the received symbols, the y1 and y2, we have to decode them with the help of map decoding algorithm, and based on the decoding decisions we have to find probability of error. And that probability error, what finally you are going to get, of course that will be the minimum probability of error that is possible for the given binary system, you can understand. Okay, so this optimum detection algorithm means map detection algorithm is used to minimize the probability of error. Okay, so it will give you the best possible decisions in decoding process, so that probability of error is going to be minimized. Fine, it's okay. Now, so I'm taking first, I'm assuming let y1 is received. Let y1 is received. Okay. So to receive as y1, to receive y1, two possibilities will be there. One possibility is x1 emitted and x1 received as y1. It is one possibility to receive y1 at the receiver side. X1 to be emitted, and that emitted x1 should be received as y1. So this is one possibility to receive y1 at the receiver side. Okay. What is another possibility for y1 is x2 emitted and that x2 received as y1. It is another possibility for y1. Okay. Now, so if you substitute the respective values, px1, this is, let y1 is received. Fine. So px1 is how much? 0.4. Py1 by x1 is 0.6. Okay. Px2 is 0.6. Py1 by x2. What is Py1 by x2? 0.8. Okay. So this is. So now tell me, to receive y1, is x1 having the highest possible chances or x2 having highest possible chances? I can say x2 having highest possible chances. Okay, 48% chances are there. Here 24% chances are there. So to receive y1 at the receiver side, x2 having the highest possible chances. So here it is less than here. Then what it means is y1 decoded as x2. Whenever we receive y1 at the receiver side, then that y1 now will be decoded as x2. Okay, because to receive y1 at the receiver side, x2 having the highest possible chances compared to x1. So that's what y1, it is definitely a wise decision to decode y1 as x2 here. Now let y2 is received. Y2 is received. So let's decode y2 here. Yes, to receive y2, two possible chances. What are the two possible chances? x1 emitted, x1 received as y2. Another possibility is x2 emitted and that x2 received as y2. These are the two possible chances to receive y2. And if you substitute the values here, px1 is 0.4 and py2 by x1. What is py2 by x1? 0.4. This is, yes. And px2, of course, 0.6. And py2 by x2. What is py2 by x2? 0.2. This is 0.2. Now, to receive as y2, x1 having 16% chances and x2 having 12% chances. So to receive as y2, x1 having the more chances here. So here it is greater than, you can see. So to receive as y2, x1 having the highest possible chances compared to x2. So here y2, this is decoded as x1. y2 decoded as x1. Okay. Now based on this decoding decisions, we have to find probability of error. Okay. So let's first check what is the probability of no error. I'm denoting that with PC. So in this process of decoding, what are the chances of no error? Means if you decode like this, what will be the chances for no error? We will try to see that first. Okay. The first decoding decision from this algorithm is y1 decoded as x2. Now let's see, okay, whether this decision from the algorithm is correct or not. This decision given by the algorithm is correct or not. Let's check that. Yes, the received y1 is due to x2. Yes, the received y1 is due to x2. Yes, it is correct only. The received y1 is due to x2. But with how much percent chances? 48% chances. 48% chances. So this decision given by the algorithm, yes, it is correct with 48% chances. Means if you decode like this, then with 48% chances, no error, I can say. Okay. What is another decision given by this algorithm is y2 decoded as x1. Okay. Now let's check the validity of this decision. Okay. Means this decision given by the algorithm, is correct or not? If correct, then with how much percent chances it is correct? Let's check that. Yes, the received y2 is due to x1. Yes, the received y2, yes, it is due to x1, but with how much percent chances? 16% chances. So this decision given by the algorithm, okay, yes, it is correct, is of course correct, but with how much percent chances? I can say 16% chances. 0.16. So this is 0.64. Okay, means if you decode like this, then among 100 symbols you decoded the receiver side, for 64 symbols no error you can expect. For 64 symbols no error in the decoding in the decoding process, provided you decode like this. In this case, among 100 symbols we decoded the receiver side, for 64 symbols I can say no error. 64 symbols के लिए no error means then remaining 36 symbols के लिए definitely error will be there. Means in this decoding process, what will be the chances for error? That is 1 minus PC, that is 1 minus 0.64, this is 0.36. Okay, means by using optimum detection algorithm, map decoding algorithm, the probability of error will be 0.36. Okay, 0.36. So here option B will be correct. 0.36. Okay. Mega Agrawal, sir, particular detection techniques not mentioned. Then in that case, map detection only we have to use. The default will be map detection only we have to use. Okay, yes. Keep answering in the chat box. Okay. Some of you okay, are getting confused, giving some wrong answers. Okay, be careful. Okay. Now, now if you see this question here, this is MSQ type question, multiple select type question. This is okay. Multiple select type question means here one or more options can be correct. Here one or more options can be correct. Okay. Now I really want to check how many of you will give correct answer for this. This is definitely a good question here. So I want to see how many of you will give correct answer for this. Now, joint WSS random processes XT and YT. Okay. So first I want to let you know about joint WSS random processes. Joint WSS random processes means here XT and YT are individually WSS random processes should be. Okay, when you can say a random process is WSS random process, the mean and AC of both should be constant. Okay, so mean and AC of both should be independent of time. In that case, you can call that random process as WSS random process. Okay, now here XT and YT individually should be WSS random processes. At the same time, if you see the cross correlation between them, the cross correlation between XT and YT, that is RXY tau, this is cross correlation between them. That cross correlation function also should be independent of time, means should be function of tau only, means should be independent of t, should be independent of t. In that case, I can say those two random processes are jointly WSS random processes, I can say. Yes, when you can say two random processes jointly WSS random processes, when you can say both random processes individually WSS random processes होना चाहिए, individually should be WSS random processes. At the same time, the cross correlation function between them also should be independent of time. Okay, in that case, the given random processes, yes, you can call them as jointly WSS random processes, you can call. Fine. Okay. Okay. XT and YT define a process W of t by, okay, these two random processes XT and YT defining a new random process W of t. XT cos omega naught t plus YT sin omega naught t. Fine. Where omega naught is a real positive constant. This omega naught is a constant. For W of t to be WSS random process. Now for this new random process W of t to become a WSS random process, which of the following condition is or are to be satisfied? It is MSQ type question. One or more options can be correct. Only one option can be correct, or multiple options also can be correct. Okay. So which of these conditions should be satisfied? Okay. So that W of t will become a WSS random process. When you can call W of t WSS random process wide sense stationary random process. WSS I mean to say wide sense stationary. Okay, fine. So I can call this W of t as wide sense stationary random process provided mean and AC of both should be independent of time. Okay, then I can say W of t is WSS random process. So mean should be independent of time and ACF also should be independent of time. Okay, to make those conditions satisfied. So which of these options we have to maintain, which of these options to be satisfied, okay, to make that W of t WSS random process, we have to see. Fine. Now yes, so what is W of t given? XT cos omega naught t plus YT sin omega naught t. Okay. Now first I am finding the mean. Mean should be independent of time now. So let's find mean. Okay, so expectation of W of t is equals to, so here xt and yt only random processes, except xt yt all other signals, this cos omega naught t, sin omega naught t, you can see them as deterministic signals only, because xt and yt only random processes here, except xt yt everything else, yes, we consider as a deterministic signal only. And expectation of deterministic signal is same signal only, expectation of deterministic signal, you will get the same signal. So I can write cos omega naught t, this is, so this expectation I can apply only to x of t, I can apply, and I can write cos omega naught t outside, I can write, plus expectation of yt and sin omega naught t, yes, you can write outside. Okay, now fine. So here the mean should be independent of time. Okay, here you can see the terms which are function of t here. Okay, but for W of t to be a WSS random process, the mean should be independent of time. Mean should be independent of time. So to make this mean to be independent of time, okay, you have to make sure of expectation of xt should be 0 and expectation of yt also should be 0. That is the only possibility we have. Okay, to make this mean independent of time, expectation of xt should be 0 and expectation of yt also should be 0. Okay, so this here, if expectation of xt is 0 and at the same time expectation of yt is 0, then the mean of W of t will become 0. I can see the mean is independent of time. Okay, so this is one condition to be satisfied here. Expectation of xt should be 0, expectation of yt also should be 0. Expectation of xt should be 0, expectation of yt also should be 0. So option A is correct. Okay, fine. Now what about ACF? Second one is ACF also should be independent of time now. ACF of W of t. So I can use the formula expectation of WT1, okay, into WT2. This is, you can use this formula. Expectation of product is nothing but correlation, it is autocorrelation. Or as I said, you can use this formula also. Expectation of W of t into W of t plus tau. You can use this formula also. Okay, but for mathematical convenience, it's better to use this formula. Okay. And of course, in this, whenever you're dealing with correlation function, you can use this t1, this t1 variable and t, and t2 and t plus tau. You can use these variables interchangeably. You can use. Okay, t1 and t, this is, and t2 and t plus tau, you can use these variables interchangeably, can be used when you're dealing with correlation function. Okay, now if you substitute the values here, this is expectation of W of t1. W of t is what? Xt cos omega naught t plus yt sin omega naught t. Okay, now W of t1 here, W of t1, in place of t you will get t1 here. So this is xt1, this is cos omega naught t1 plus yt1 sin omega naught t1. This is okay, into W of t2 here, W of t2, in place of t just write t2, you can write. So now it will be, yes, xt2 cos omega naught t2 plus yt2 sin omega naught t2. This is, let me check the chart box once. Kusum Raj Purohit, ABC. Samskar, ABC. Swati Yadav, ABC. Pavitra Gowda, ABC. Swarup Rath, hi sir, old student. Do you remember once I had come to attend your class at Delhi Center and asked you for your autograph after the class? Yeah, I think, Swarup, nice to meet you. I hope you're doing fine. I expect everyone is fine. Okay, I hope for that. Okay. Proceed further. So multiply, do that complete multiplication and apply expectation to every term. Okay, yes, do that. Yes. Yes. Do this complete multiplication. Now if you multiply these two terms, now this is I'm multiplying these two terms, then this will be multiply and apply expectation also. Then what you can expect is expectation of xt1 xt2, this is okay, and you can add cos omega naught t1 and cos omega naught t2 outside of expectation you can write, because except xt and yt everything else you can see as deterministic signal only, and the deterministic signals you can write outside to expectation you can write. So this is cos omega naught t1 cos omega naught t2 you can write, this is okay, plus expectation of, if you see these two terms here, xt1 yt2, okay, this is xt1 yt2, this is cos omega naught t1 sin omega naught t2, this is I'm writing outside cos omega naught t1 sin omega naught t2, plus if you see these two terms here, expectation of yt1 xt2, this is yt1 xt2 sin omega naught t1 cos omega naught t2 sin omega naught t1 cos omega naught t2, plus finally we left with this term. Just multiply this with this, then this is expectation of yt1 yt2, this is sin omega naught t1 sin omega naught t2. So these are the terms what you got. Okay, now if you expand it, this is what you can expect is this cos a cos b cos a plus b plus cos a minus b by 2. Just do that expansion, then what you can expect is, I'm going to do that expansion, expectation of xt1 xt2, expectation of xt1 xt2 means it is autocorrelation function of xt only. Okay, autocorrelation function of xt, I'm writing this is rx tau, this is okay. It is clearly given in the question that okay, here xt and yt, these are jointly WSS random processes. Xt and yt both are WSS random processes. WSS random process means the mean and ACF are independent of time. Independent of time. So here, yes, so here it is autocorrelation function of xt, this is, then I can denote with rx tau, because xt is, it is given WSS random process. WSS random process means ACF is a function of tau only, I can say. ACF is function of tau. So I can denote with Rx tau, I can denote with cos A cos B, cos A plus B plus cos A minus B by 2, cos A plus B. So A plus B means omega naught T1 plus T2. Okay, omega naught T1 plus T2. T1 plus T2 you can write 2T plus tau. So I'm transforming to T and tau variables. Like T1 you can replace with, this is T, T2 replace with T plus tau. Because what is my requirement is, what is my ultimate requirement is the ACF of this W of T should be function of tau only, should be independent of T. So that's what I'm transforming completely to T and tau terms I'm transforming to. Okay. Now then T1 plus T2, T1 plus T2 you can write 2T plus tau, you can write T2 minus T1 you can write tau, you can write T1 minus T2 you can write minus tau, you can write like that. Okay. Now fine. Cos A cos B, cos A plus B plus cos A minus B by 2. By 2 I'm writing outside, plus cos A minus B, cos omega naught T2 minus T1 or T1 minus T2, because cos minus theta will be cos theta only. So cos omega naught T2 minus T1 means tau. This is the first term. This is plus R xt1 yt2. It is a cross correlation between xt and yt. Cross correlation between xt and yt. This is, okay. It is jointly WSS random process. That is also given in the question. Xt and yt jointly WSS random process. Jointly WSS random process means that the cross correlation function also will be independent of time. The cross correlation function also will be function of tau only. So it is a cross correlation between xt and yt. So I can denote this with R, X, Y, tau, I can denote with. Cross correlation function also function of tau only, you can understand, because it is jointly WSS random processes. Okay. Now this is sin A cos B, sin A plus B plus sin A minus B by 2. I'm writing by 2 outside. Okay. Sin A plus B, sin A cos B, sin omega naught. This is A plus B. A plus B means 2T plus tau, plus sin A minus B. Sin A minus B means sin omega naught T2 minus T1. T2 minus T1 means tau. This is the second term. Plus, what about the third term? It is a cross correlation between yt and xt. So this is, okay, this is R yx of tau. The notation I can use is, okay. So in which direction you are looking for correlation, that makes the difference between Rxy tau and Ryx tau. This is, I'm looking from x to y, here I'm looking from y to x. Okay, so I'm denoting with Ryx tau. This is, so it is Ryx of T2 minus T1. Ryx of T2 minus T1. T2 minus T1 is tau. It is Rxy of T2 minus T1. Rxy of tau. This is, okay, by 2 I'm writing of course I'm writing. This is, it is sin A cos B, sin A plus B plus sin A minus B by 2. Sin A plus B, sin omega naught 2T plus tau, sin A plus B, plus sin A minus B. Sin A minus B means sin omega naught T1 minus T2. Sin A cos B, sin A plus B plus sin A minus B, sin omega naught T1 minus T2. T1 minus T2 means minus tau. Sin minus tau means you can add minus, you can add outside. So minus sin omega naught tau. This is sin A cos B, sin A plus B plus sin A minus B by 2. Sin A minus B means sin omega naught T1 minus T2. T1 minus T2 minus tau. I'm writing minus tau. Minus outside I'm writing. Okay. So finally, so we left with this term. This is, okay. It is autocorrelation function of yt. This is R y tau by 2. This is, okay. Sin A sin B, cos A minus B minus cos A plus B by 2. Cos A minus B, cos A minus B minus cos A plus B by 2. Cos A plus B by 2. A plus B means omega naught T1 plus T2. T1 plus T2 means it is 2T plus tau. This is, This is what you can write. Sin A sin B cos A minus B minus cos A plus B. Minus cos A plus B. Okay. Now, so now I can summarize like this. Okay. Now it is equals to. So here you can see cos omega naught tau. If you take that cos omega naught tau common, this is cos omega naught tau. Or let me write this. If you take cos omega naught tau common, Rx tau by 2 plus Ry tau by 2. So this is Rx tau by 2 plus Ry tau by 2. This is into cos omega naught tau. This is one term. Okay. Next, if you take sin omega naught tau, the sin omega naught tau term, if you take common, then what you can expect is, yes, plus if you take sin omega naught tau common, Rxy tau by 2, or if cos omega naught tau by 2, if you take common, better. This is okay. This is Rx tau plus Ry tau, you can write like this. Okay. Then if you take sin omega naught tau by 2 common, this is Rxy tau, this is minus Ryx tau. This is okay. This is sin omega naught tau by 2. This is okay. Next, if you take cos omega naught 2t plus tau, this is this cos omega naught 2t plus tau. If you take common, what you can get, Rx tau minus Ry tau you will get. This is so Rx tau minus Ry tau. This is so this is taking which term common, cos omega naught 2t plus tau by 2. Okay, and we left with that sin omega naught t plus tau term we left with. Yes, not this sin omega naught 2t plus tau. If you take common, Rxy tau plus Ryx tau, Rxy tau plus Ryx tau you will get. This is so this is Rxy tau plus Ryx tau. This is, and this is sin omega naught 2t plus tau by 2. This is what we left with. Okay. Yes. Okay. Now, for W of t to be a WSS random process, this ACF, what you see, the ACF of W of t, this what I am calculating here is, this is ACF of W of t. This ACF of W of t should be independent of time, should be independent of t terms. So here you can see these are the t terms you see here. This is t term here, this is t term. Okay. So here these are tau terms here. You can leave these terms. We have no problem with these terms, with these first two terms. Okay, because only tau terms you can see. But we have problem with these last terms, because you can see the terms here which are function of t here. Okay, and for our requirement is this ACF, what we are finding for W of t should be independent of time. Okay, so this term should be vanished and this term also should be vanished. Okay, for this Rx tau should be equals to Ry tau, that is this Rx tau should be equals to Ry tau. Then this term will be vanished. Okay, so Rx tau should be equals to Ry tau. And at the same time, this Rxy tau should be equals to okay, minus of Ryx tau. This term also we have to vanish this. We have to vanish this term also. We have to nullify this last term also. To nullify this last term, this Ryx tau should be equals to, this is Ryx tau is equals to minus Rxy tau. So these two conditions should be satisfied now. If these two conditions satisfied, then I can say the ACF also, this ACF of W of t also independent of time, I can say. Okay, then W of t will become WSS random process. And one thing here, this is one property of autocorrelation function. What the property is, Ryx tau is equals to Rxy of minus tau. It is a property of cross correlation function. Okay, Ryx tau is Rxy of minus tau, or Rxy of tau is Ryx of minus tau. You can write this is Rxy tau is equals to, this is Ryx of minus tau. Okay, or you can write like this also, Ryx tau is equals to Rxy of minus tau. This is the property of cross correlation function. So this Ryx tau, you can write Rxy of minus tau, and it should be equals to what this is, minus Rxy tau. This is, you can rewrite this condition like this. So simply what you can understand is this cross correlation function should be odd function here. Rxy of minus tau should be equals to minus Rxy of tau. This cross correlation function should be odd function. Yes, this is the condition what we got. So I'm rewriting like this. How I'm rewriting is, yes, we know that Ryx of tau, you can write Rxy of minus tau. This is the property of cross correlation function. So Rxy of minus tau equals to minus Rxy of tau. Okay. Now see. So which of the options will be correct here? This is, yes, this is a lengthy question definitely. Yes, this option B also should be satisfied. Rx tau should be equal to Ry tau. Next, Rxy minus tau equals minus Rxy tau. Yes, this condition also should be satisfied. Rx tau equals to minus Ry tau. No, this is incorrect. Rx tau should be equal to Ry tau. I know this is. Okay, Rx tau should be equal to Ry tau. Then only this term will be nullified. Okay, but option D is given as Rx tau equals to minus. Okay. Minus Ry tau is given. That is of course incorrect. So here I can say A, B and C will be correct here. Okay, A, B, C will be correct. So those who are copying this, you can check this once. Those who given correct answers for this, it's so good. Those who given correct answers for this, I'm very happy for those who given correct answers for this. The given correct answer for this means they are preparing very well, is what I can understand. Their preparation is good. Ankita Duggal. Okay. I think Samskar Sharma. So I know these names. Okay, I come across these names. I hope. Okay, your current session students only. I think most of you. Okay, very good. Now, you see the next question. This is a question from analog communication. So I'm trying to solve most of the questions from digital communication only, because most of the questions they're asking in digital communication nowadays in GATE examination. That too from random process they're asking. So that's what I concentrated much on the topic of random process in this GTQ series. Okay, in this GTQ course. But okay, we'll do some questions from analog communication also. Yes, if you see this question. A sinusoidal message signal of, this is easy question. Okay, sinusoidal message signal of 2 volts, 10 kilohertz. Okay. Sinusoidal message signal means the default you can understand as cos 2 pi fmt, am cos 2 pi fmt, and here amplitude is given and frequency given. So here amplitude of message signal is 2 volts and frequency given 10 kilohertz. I think you can easily give the answer to this question, I hope. Okay, let me little enlarge this. Okay. And this message signal is frequency modulated by sinusoidal carrier signal. This is sinusoidal carrier signal of having frequency 1000 kilohertz. Sinusoidal carrier signal means you can we treat that as cos 2 pi fct, AC cos 2 pi fct, and what is the frequency given? 1000 kilohertz. So fc given 1000 kilohertz. Sensitivity constant of frequency modulator is 30 kilohertz per volt. Sensitivity constant of frequency modulator, you can understand this is frequency sensitivity constant only, that is kf. Kf value is given, that is 30 kilohertz per volt. The resultant FM signal is passed through ideal bandpass filter. Okay, it is passed through the resultant FM signal passed through ideal bandpass filter with center frequency 1000 kilohertz and having bandwidth of 70 kilohertz. Okay, so this is what you can understand is, okay, the bandpass filter you can understand like this. If you see the bandpass filter, so it is having center frequency of 1000 kilohertz and bandwidth of 70 kilohertz. Okay, it is the transfer function of the filter, what you can understand. Okay, bandwidth of that 70 means from it allows from which frequency to which frequency. You can understand this is 1000 plus 35. Okay, this side this will be 35 and this is 35. 1000 plus 35, this is 1035. Okay, now 1000 minus 35, this is 965, this is kilohertz. Okay, 965. So it is allowing from 965 to 1035 kilohertz is what you can understand. These band of frequencies allowed by the filter. Okay, now then the highest frequency component that will present at filter output is dash kilohertz. So it is numerical answer type question. So what is the highest frequency that will present at filter output? Okay, so here the FM signal, this I'm denoting with SFMT, is given to band pass filter. Then what is the highest frequency that will present at filter output? We have to find out. Okay, now actually if you see the what is the highest frequency that will present at filter output, we have to see the spectrum actually. Okay, so what is the spectrum of FM signal we have to see. Okay, so the spectrum will be like this. Yes, if you see the spectrum, the FM spectrum, if you recall, it is FC, okay, FC plus FM, FC plus 2 FM, FC minus FM, FC minus 2 FM, and this is, let's go on like this. This is FC plus 3 FM, this is, and FC minus 3 FM, and FC plus 4 FM, FC minus 4 FM, and it's go on. Okay, and actually this data which is given to us, the KF value is given. Okay, this is actually this is not useful in solving this question. This is some extra data only is given to us. Okay, because to solve this question, just we are interested in the spectrum of FM signal, means which frequency is present in FM signal. That is only our interest. Okay, and yes, we know that in FM signal which frequency is present, FC plus minus FM, FC plus minus 2 FM, FC plus minus 3 FM, FC plus minus 4 FM, and it's go on. So all these frequencies present in this FM signal. Okay, now, yes, this is generally what you can expect in FM spectrum is the strength of higher ordered sidebands will go on decreases like this. It's generally what you can expect, and it's go on. Okay, and if you substitute the values here, FC given how much in the question? FC given 1000 kilohertz. Okay, and FM, what is the message frequency given? Message frequency given 10 kilohertz. Okay, this is 1010 kilohertz, 1020 kilohertz, 1030 kilohertz, 1040 kilohertz. This is 990 kilohertz. This is 980, 970 and 960 kilohertz, and it's go on. And this FM signal passed through band pass filter, and the specifications of band pass filter of course given. The pass band is centered about 1000 kilohertz and allowing from 965 kilohertz to 1035 kilohertz. So this is, it is allowing from, this is 965, this is to 1035 kilohertz. This is 1035, you can see somewhere in between here. This is okay. Now after passing through this band pass filter, yes, it is allowing up to 1035 kilohertz. This is. Now at the output of band pass filter, what is the highest frequency that will present is 1030 kilohertz that will present. Means these frequencies will present at filter output from 970 kilohertz to 1030 kilohertz. These frequencies will present at filter output. Now what is the highest frequency present at filter output is 1030 kilohertz. Okay, the highest frequency that will present at filter output is 1030 kilohertz. Okay, then yes, what is the answer here is 1030. 1030. So Ankita Duggal, okay, fine. Yeah, Ananya, okay, fine. Yeah. So Kush, it's not 1006. So most of some students given 1006 answer, that is incorrect. Okay, fine. Now if you see the next question. Yes. Yes, if you see this question is related to information theory. Yes, here a discrete memoryless source emits three symbols S0, S1, S2 with probabilities 1 by 4, 1 by 4, 1 by 2 respectively. Okay, so here the source is denoting with S, it is emitting three symbols S0, S1, S2, and with the probabilities. So that probability is given as PSI is equals to, what the probability is given? 1 by 4, 1 by 4, 1 by 2 respectively. Okay. Now entropy of second order extension of this source will be how much? We have to find out. Okay. So entropy of second order extension of this source we have to find out. Okay. So actually how to understand this is, if you find the entropy of the given source HS, first order extension or simply first order source, I can say first order, so entropy of the first order, simply entropy of the source or entropy of the first order. Okay, this is the formula we know, this is summation I PSI, this is log 1 by psi base 2. It is a formula. Now if you substitute, first I am finding for first order extension, I am finding the entropy. So after this we will proceed for second order extension. So उसके लिए entropy क्या होगा? We will proceed for that. So 1 by 4 log 4 base 2 plus 1 by 4 log 4 base 2 plus 1 by 2 log 2 base 2. And if you do this, you will come to know this is 3 by 2. This is bits per symbol. Okay. Okay. So here, what actually it means is entropy of the first order means in the process of source coding. In the source coding, what we do is, okay, to transmit these symbols, the source is emitting these symbols. In transmitting these symbols, first we encode these symbols. Okay, every of the symbol we represent with a unique binary code. S0, S1, S2, every of the symbols we represent with a unique binary code, and that codes will be transmitted. Okay. So first order extension of the source means the individual symbols will be coded. If the individual symbols are coded, that is called as first order extension. And if you group the symbols, if the grouping of the symbols, if you go for grouping of the symbols, and the grouping of the symbols are coded, okay, then that leads to second order extension, third order extension, fourth order extension, like that. Okay, so to minimize the average code length means in this coding process, in the coding process, okay, each symbol, okay, represented by how many bits, that is called as average code length. Averagely each symbol represented by how many bits, that is called as average code length. So to minimize that average code length, we always look for the average code length should be as low as possible. So to minimize that average code length, okay, so we go for this extension of the source. Okay, the coding of the extension of the source we will go for. We'll go for grouping of the symbols. Okay, and we call them as blocks, like, and we go for block wise coding instead of symbol wise coding. We go for block wise coding, and if you go for block wise coding, the average code length will be minimized. So if you see second order extension source means I'm denoting with S square. This is second order extension source. Okay, so here if you see the symbols corresponding to this second order extension, okay, so what are the symbols corresponding to the second order extension? I'm giving some new names, like sigma naught, sigma 1, like this, sigma 2, like this. Okay, it is second order extension. Now let's see the symbols corresponding to, okay, so this is, what about corresponding symbols of S? What are the corresponding symbols of S? So I mean to say this is S0, S0. Like if you see the source S here, it is emitting symbols like S0, S0, S1, S2, S1. The symbols are emitted in random sequence. In random sequence, the symbols will be emitted. So instead of coding the individual symbols, we form the grouping of the symbols, S0, S0, S1, S2, like that. So I'm going for grouping of the symbols. So this grouping of the symbols will be coded like S0, S0 I will code with 0, 1, 0, or S1, S2 I will code with like 1, 0, 1, like by using Shannon-Fano coding, Huffman coding. We go for coding of the symbols after grouping here. After grouping, we will go for coding. So instead of symbol wise coding, we are going for block wise coding. Okay, this S0, S0 we will code like this. S1, S2 will code with some code like that. This is called as, okay, extension of the source. Okay, so I'm going for second order extension. If you go for second order extension, how many combinations possible now in this process of blocking of two symbols? How many different blocks possible? I can say 8 different blocks will be possible, like S0, S0, like S0, S1, S0, S2. Okay, next S1, S0, S1, S1. Now it's go on. Finally S3, S3. 8 different blocks are possible now. 8 different blocks. I'm denoting with 9 different blocks. 9 different blocks. Okay. For S0, starting with S0, 3 blocks possible. Starting with S1 also 3 blocks possible. Starting with S2 also. S2, no? S0, S1, S2 I'm denoting with. Fine. I'm denoting with S2. Okay. Starting with S2 also 3 blocks possible. Altogether 9 blocks possible. Okay. Now, yes, it is just like a formula also. You can say this. This is how many symbols here? 3 symbols, no? So if you see 3 symbols, M I am denoting with. I'm going for second order extension. Second order extension means n equals to 2. Number of symbols available with the source I'm denoting with M, and I'm going for second order extension. Then how many blocks possible will be M power n blocks will be possible. M power n different blocks will be possible. In this case 3 square I can say. So 3 symbols available here. I'm going for second order extension. 3 square means 9 blocks possible here. Okay, fine. Now, see, the coding will be done based on the probabilities. In the source coding, okay, we do the coding based on the probabilities. So let's see what are the corresponding probabilities. P sigma I. What is the probability for this block to be emitted? S0, S0. What is the probability for S0 to be emitted? S0 to be emitted, 1 by 4. Okay. So here the symbols which are emitting here are independent from one another. Independent. Okay. The current symbol which are getting emitted, it is definitely independent of what is the previous symbol which is emitted. It's nowhere depends on what is the previous symbol which are emitted. So the symbols which will be emitted independently, of course. Okay. So that's what. So what is the probability for this combination S0, S0? What is the probability for S0? 1 by 4. What is the probability for S0? 1 by 4. Both are independent. Here symbols will be emitted independently. Occurrence of 2 independent events simultaneously. What is the probability of occurrence of 2 independent events simultaneously? That is multiplication. So 1 by 4 into 1 by 4. This is, so this is 1 by 4 into 1 by 4. The probabilities. This is 1 by 16. Next. S0, S1. This is 1 by 4. What is the probability for S1? S1 also 1 by 4. Like this. And this is 1 by 4 into 1 by 2. This is. And S1. S1 is 1 by 4. S0 is 1 by 4. Like that you will get the probabilities. Okay. This is the probabilities you will get. Like this. Okay. Now based on these probabilities we have to find entropy. To find the entropy we just need the probabilities we need, that's it, to find the entropy. So in this process of second order extension 9 different blocks are possible, and the corresponding probabilities these are. Okay, and based on these probabilities we have to find entropy. Okay, that is the entropy of the second order extension source. H of S square I am denoting with. Okay, so it is the formula summation P sigma I, that blocks I am denoting with the sigma here, and log 1 by P sigma I base 2. Okay, just 9 probabilities you have now. So this is you can take I is equals to 0 to 8. You can take this is I is equal 0 to 8, and you can substitute this probabilities 1 by 16 log 16 base 2 plus 1 by 16 log 16 base 2 and 1 by 8 log 8 base 2, like that. Okay, so if you substitute that, okay, finally you will come to know. So I already done this calculation. Okay, you will come to know this is 3 you will get. This is, you just try this, 3 bits per block. This is, so it is entropy of the second order extension source. But students, in the examination to get the entropy of the nth order extension, it is second order extension, that's okay. And if at all he is asking for third order extension, how many combinations possible? Third order extension means 3 power 3. So 27 combinations are possible. Then that becomes very lengthy. Okay, so that's what one formula is there here. One algorithm is there. What that is? This entropy of the easiest way to find entropy of the nth order extension, and how to find is this H of S square is simply equals to 2 into H of S. This is simply equals to. Okay, and it will be equals to 2 into H of S is how much you got? 3 by 2. So this is 3. So it will work. Okay, if at all is asking entropy of the third order extension, if the question is h of s cube. So this is simply 3 into hs. Okay, and like that it will work actually. You can extend this for the next higher orders also, you can extend this. Okay, so it is one trick you can use to find the entropy of the higher order extension of the source in easiest way. Okay, yes. Yes, if you see the next question, we'll do the next question. Yes, see this. So try this question. Yes, let me check the chat box once. Yes. Yes, Shivam Shukla, h of x power n is n into h of x. Yes. Okay. Now if you see this question, a WSS random process xt, okay, having powered spectrum means powered spectral density only, Sx of omega equals to 72 pi del omega plus 8 by 9 plus omega square all square. So it is a powered spectral density of a WSS random process xt is given. Okay, and this is applied to a network with impulse response h of t equals to 5 into e power minus 2 mod t. Okay, then the mean of the response yt is, we have to find out. So here, this is one important model of question. Here a random process xt is given to a network, is given to a system whose impulse response is 5 into e power minus 2 mod t. Okay, and the response is yt. Okay, now for this xt, the power spectral density of xt is given. Sx of omega is 72 pi del omega plus 8 by 9 plus omega square all square. This is okay. The power spectral density of xt is given, and we have to find the mean of this yt. We have to find out. Okay, now because it is clearly given WSS random process, the input is okay. Now with this impulse response, yes, you can see this as LTA system only, it corresponding to, and we are dealing with WSS random process here. Then output mean directly you can write as input mean into h of 0. This formula can be used. Output mean equals input mean into h of 0. H of 0, yes, we can easily find out. Let's find out the input mean. Okay, so this model of questions already given in competition exams. Okay, relating output mean with input mean. But how this is different is, here input mean is not directly given. Here the power spectral density of xt is given, and from this power spectral density of xt, we have to find the mean of xt. This makes the difference. Okay, so anyone, what is the mean of xt? Can anyone? I just want to hear the answers from you. Yeah, some students already given answers. 30, very good. Ankit Yadav, Pavan Kumar, very good. Deepshika, 30 is the answer. Yes. Yes, what is the mean of xt? How to find this is, yes. First, if you try to find DC power, DC power is nothing but mx square. Mx means, I mean to say the mean of xt. Okay, it is clearly given WSS random process. Xt is WSS random process. The mean is independent of time. The mean of xt I'm denoting with mx. The mean will give you DC value. This mx, the mean will give you DC value only, and square of DC value will give you DC power. Okay, so first let's find out DC power, because the power spectral density of xt is given. From this power spectral density we try to find power. Okay, how to find power from power spectral density? The area under PST. The area under power spectral density will give you corresponding power. Okay, now here, how to get DC power? DC power means the power distributed to the DC frequency component. Here DC frequency component means omega equals 0. This is. See, if you plot Sx of omega versus omega, this omega is equal 0 corresponding to DC frequency component. DC frequency component. What is the power of, what is the frequency of DC? Frequency of DC will be 0 only. And this 0 hertz, or I mean to say 0 radians per second, you can call this as a DC frequency component. So the power distributed to this DC frequency component we call as DC power. Okay, now how to find the power distributed to this DC frequency component? How to get that? The area under PST will give you power. So you have to see what is the area under PST at omega is equal 0. Area under PST at omega is equal 0, that will give you the power distributed to this DC frequency component. So here this DC power is nothing but this is, okay, area under, this is area under Sx of omega at omega is equal 0. What is the area under Sx of omega at omega is equal 0 will give you the power distributed to this frequency component omega is equal 0. The power distributed to this DC frequency component is nothing but DC power. And one thing is, here the PST is given in omega domain, then that's what you have to divide with 2 pi. Okay, what is the area under PST? Divided by 2 pi, that will give you the power. Okay, if at all PST given in F domain, normal F domain, simply area under PST will give you power. But here PST is given in omega domain, so the area under PST, and you have to divide that by 2 pi, that will give you the corresponding power. Okay, now this will be, see this, what is the area under this PST at omega is equal 0? This is, you can see the impulse function will exist. If you plot this Sx of omega, this is, if you plot this Sx of omega at omega is equal 0, you can see the impulse function, you can see. And with area how much? 72 pi. This is, if you plot Sx of omega, you will see definitely impulse function, you will see, okay, at omega is equal 0. And the 72 pi specifies the area only, the area under this impulse function at omega is equal 0. Okay, this 72 pi is the area only. Okay, so what is the area under this PST at omega is equal 0? That is 72 pi only. This is the area here, 72 pi. So it will be, so it is not having any significance. Okay, so in finding the area under PST at omega is equal 0, it is not having any significance. So this existence of impulse function at omega is equal 0, this is what you have to concentrate. So the area under PST at omega is equal 0, 72 pi. So this is 1 by 2 pi into 72 pi. This is, okay. Okay, this is 36 now. How much you will get here? Yeah, 36. This is, yes, this mx square is 36. Then what is the mean? Mean mx will be 6 now. This is, it is the input mean what we got. This is, we need the mean, input mean we need. Okay, so mx we got. Then we have to find h of 0. Output mean is input mean into h of 0. So h of t is what? 5 into e power minus 2 mod t. Okay, this is, so h of t, it is 5 into e power minus 2 mod t. Okay, then what is the Fourier transform to this? H omega is equals to, I think you know it, e power minus 2a mod t. Okay, what is the Fourier transformation is 2a by a square plus omega square. Okay, so from this is 2 into 2 by, okay, a square means 4 plus omega square. So this is 20 by 4 plus omega square. Then if you see h of 0, in place of omega substitute 0, 20 by 4 will be 5. This is. So output mean is equals to input mean into h of 0. This is 6 into h of 0. This is 30. Okay. 30 will be the answer here. Okay. So let me check the chart box once. Yes. Yeah, this is a good one. Bashir is asking, mean can be plus 6 minus 6. Yes, I'm accepting that. Okay. So if at all, yeah. So that's what, yeah, the mean actually can be, one of your friend asking, can be minus 6 also. Yes, that possibility is also there. The mean can be minus 6 also. So that's what, if at all, in numerical answer type question, you don't actually, I given this as a numerical answer type question. In GATE examination, they will take care of this also. They will give this as a multiple choice question only. They will make this a MCQ question only, and he will give options such that the options will be matched either with 6 or either with minus 6. Okay, don't think like the options will be matched with 6 and minus 6 also. They don't create the confusion like that. Okay, so this question, okay, if at all this question is given, you expect this question as MCQ type question only. They don't give that as a numerical answer type question, because the confusion will be there for numerical answer type question, of course, because the mean can be minus 6 also. I'm accepting that. Okay, so if this question is given, you can expect this as MCQ type question only. Okay, and the options, he will frame the options such that the options will be matched either with 6 or minus 6 only. Like that only options will be framed. Okay, fine, good one. Yes, if you see this question here, Mega Agarwal, spectral density के second term का DC value find out होगा? No chance, no. Mega Agarwal, see this? If you see this second term, if you see, even if you plot it, okay, if you plot it at omega is equal 0, even if you plot this is at omega is equal 0, what you will get? This is 8 by some 91. You will get some value. You will get, that's it. You will get some value. This is okay. This is, as omega increases, the value is decreases. It's going to be something like this. Even if you plot this second term also, it's going to be something like this. At omega is equal 0, this is 8 by 91. The value is 8 by 91. But what is our interest? Our interest is the area under this Sx of omega at omega is equal 0. That is what our interest is. Okay. So what is the area under Sx of omega at omega is equal 0? That impulse function only you have to concentrate. This is. And due to this, what is the area at omega is equal 0? Due to this term, what is the area at omega is equal 0? 0 only. Okay. This is. It is continuously varying. It is continuously varying. Okay. Then what is the point? What is the area of this point? That will be 0 only. So due to this second term, okay, what is the area at omega is equal 0 will be 0 only. Okay, this impulse function will give you some finite area. It will give you at omega is equal 0. Okay, the second term, okay, due to second term, the area at omega is equal 0 will be 0 only. No need to consider that. Okay, fine. Now if you see this question here, try this question. This is about SHD receiver. Super heterodyne receiver. Okay, yes. So here an SHD receiver, AM means amplitude modulation, AM SHD receiver. Okay, SHD receiver and which is of AM type, is tuned to 1200 kilohertz station. Okay, so this, what is a tuned frequency? I'm denoting with Fs. This is 1200 kilohertz. Okay, and intermediate frequency is 450 kilohertz. Okay, so IF value is given as 450 kilohertz. IF value is given. Okay, and if the lower side injection, so you have to concentrate on this term, lower side injection used for the mixer. Okay, so if you see the mixer, actually what I want to tell you here is mixer. Okay, after mixer you will see IF amplifier will be there, and it is the local oscillator. The local oscillator frequency FL I'm denoting with. The tuned frequency, the carrier frequency of the tuned station I'm denoting with Fs. Okay, the mixer is always designed to perform down conversion only. The default of this is designed to perform down conversion only. Then here two possibilities will be there. That is, you can select FL greater than Fs and FL less than Fs also you can select. Two possibilities to select FL. And if at all FL greater than Fs, the local oscillator frequency higher than Fs, then what it means is, so here higher side injection is used or upper side injection is used. What it means is higher side injection this is. And if at all this FL less than Fs, if at all the local oscillator frequency less than Fs, then what it means is the lower side injection this is. Lower side injection is used for the mixer. What it means is, so here the default we select as FL greater than Fs only. The default we select as, so if lower side injection, higher side injection is not mentioned, the default we take as FL greater than Fs only we take. It is a default we take. Higher side injection we take as default, but it is clearly given here the lower side injection is used. Okay, or he can mention like this also, the local oscillator frequency selected as lowest of the two possible values. He can mention like that also. Here FL can be greater than Fs, FL can be less than Fs. Two possibilities for FL. He can mention in the question such that the lowest of two possible values taken for FL. There is nothing but lower side injection only. And he can mention like this also. Okay, the highest of two possible values selected for FL. Highest of two possible values for FL. Two possible values, and he can mention like the highest of two possible values selected for FL. Then indirectly what it means is higher side injection is used. Okay, he can give any terminology in giving the question. He can frame the question with any terminology. But of course here FL less than Fs, lower side injection means FL less than Fs. What is given is FL less than Fs given. Okay, then what we have to find out is then local oscillator frequency of mixer and image frequency respectively will be. So we have to find the local oscillator frequency and image frequency respectively will be how much we have to find out. Okay, yes, what is the answer given? Yeah, some students given B, some students A, some students C. Okay, so some contrast is there. Okay, okay, so students are dividing between A, B, C. Okay, okay, so you're getting confused I think in this question. Okay, fine. So this here, fine. Then what is a mixer output? At the mixer output you will get intermediate frequency. This is, then IF is equals to whatever that new frequency we get at mixer output, is called as intermediate frequency, that IF equals to here FL less than Fs here, or I can say Fs greater than FL, or I can say the mixer is designed to perform down conversion only. That is the default of. Okay, down conversion means subtraction of frequencies you will get. Here Fs greater than FL, subtraction of frequencies means Fs minus FL. This is, so IF is equal to Fs minus FL. Then FL we need. FL equals to Fs minus IF. Fs minus IF means it is 1200 kilohertz minus 450 kilohertz. So this will be 750 kilohertz. Local oscillator frequency 750 kilohertz. Next, if you see image frequency. Image frequency is Fs minus 2IF. Okay. If FL less than Fs, if the lower side injection is used, the formula to find image frequency is Fs minus 2IF. So if you substitute now, this is 1200 kilohertz minus 2 into IF. IF is how much given? 450 kilohertz. So this is 300 kilohertz. Okay, this is. Or you can use this formula also, you can use FL minus IF also, this formula also you can use this. Yeah, FL minus IF. Yes, you can write Fs minus IF you can minus 2IF, you can write minus IF you can write. And Fs minus IF is what? Fs minus IF is FL only. FL minus IF also you can use. This formula also you can use. Okay. So 300 kilohertz. So 750 kilohertz and 300 kilohertz. 750 kilohertz and 300 kilohertz. So option A will be correct here. Okay. Then if at all FL greater than Fs, if higher side injection is used, FL greater than Fs, the formulas will be completely changed. Okay. If FL greater than Fs, then IF will be equals to FL minus Fs will become. If FL greater than Fs, then FL minus Fs you will get. And what about image frequency? Image frequency will become Fs plus 2IF will become. If higher side injection is used, FL greater than Fs, in that case, the image frequency will be Fs plus 2IF will become. Okay, fine. Now if you see the next question. This question is about linear block quotes. Okay, so I thought to close in 2 hours, but this is not happening. And Deepshika, if not mentioned and MSQ, we have to choose both. If at all that is given as MSQ type question, then we have to take both possibilities we have to take into consideration. If at all that is MSQ type question, and if nothing mentioned, then yes, Deepshika, you have to take both. Both possibilities you have to take for MSQ type question only. And for MCQ type question, okay, if lower side injection, higher side injection is not given, but the question is MCQ type question, then the default to the higher side injection only you have to take. FL greater than Fs only you have to take. FL greater than Fs only you have to take. Yes, Kusum, always down conversion only, no doubt in that. Okay, that is down conversion only we have to take. Yeah, Rahul Gupta, thank you. Thank you. About अच्छा पढ़ाते हो communication. Thank you, Rahul. Now, if you see this question, so it is a linear block quote. This is related to, so some little logic is there in this question. I want to tell you that logic. A systematic 7,4 LBC linear block quote. 7,4 LBC means you can compare with n, k. This is n is nothing but total number of bits in the resultant code word, that is 7, and k is number of message bits, how many bits in the message block, okay, that is 4. The number of parity bits m is n minus k, that is 3. I want to see how many of you will give correct answer for this. Okay, this is definitely a good question. This is a good question. Okay, those who will do this question, okay, definitely they are in the correct track of preparation. Definitely you can expect very good rank in examination, you can expect. Okay, good question this is. Yes. Now see this. Yeah. So here a systematic 7, 4 LBC has the parity matrix. So here interestingly the parity matrix is given. Generally till now in examination, whenever he given question for LBC, he always given generator matrix or parity check matrix is given, G matrix or H matrix is given. But here interestingly the parity matrix is given, P matrix is given. Okay. And this is the P matrix. And if 0 0 1 1 1 1 0 is valid code word, if at all this is valid code word for this given LBC, then A and B values respectively will be here. He given A and B. Okay, what this A and B values should be, okay, so that this is going to be a valid code word. So for a valid code word, okay, for valid code word C, C into H transpose equals 0. This is for valid code word C, C into H transpose will be equal 0. Okay. Now, so we have to get H matrix, we have to get. So let me try to get G matrix. Okay. Our impression is G is equals to IKP transpose. The default, what you can understand is in the resultant code word, the first k blocks will be message bits. First k bits will be message bits. And last n minus k bits will be parity bits. That is the default what you can understand. So if you take a code word, in the code word first k bits will be message bits. The last n minus k bits will be parity bits. It is the default what you can understand. Okay, fine. So if the first k bits are message bits, then that is in the form of IKP transpose. The generator matrix pattern will be IKP transpose. Okay, and IK, K is what here? K is equals to 4 here. Okay, P transpose. What is the order of P matrix here? The order of P matrix will be the parity matrix. This is 4 rows and 3 columns, 4 by 3. 4 by 3. Then P transpose, what will be the order of P transpose? 3 by 4. This is 3 by 4. So this is not a proper combination here. To write matrices side by side, okay, number of rows in it and number of rows in it should be same. Then only you can write these two matrices side by side. But in IK 4 rows are there, in P transpose 3 rows are there. So this is not a proper combination. Okay. Then what you can understand is this G, okay, it is here IKP here. This is, so it is not a proper combination. So G should be like this. G here is equals to IKP. This is IKP. This is the proper combination what you can understand. This is IKP. In regular classroom I clearly mentioned this. Okay. In writing G matrix, this notation what you say, this is actually the choice. I mean to say, it is simply the choice. Whenever you are creating a parity matrix, whenever you are talking about a parity matrix, which notation you are using, that is completely the choice. In some textbooks you will see that is P matrix, the parity matrix they denote with P matrix, and in some textbooks they denote that parity matrix with P transpose. So that notation will be the choice actually. Okay. So that's what in some textbooks G matrix you will see IKP only. In some textbooks you will see IKP transpose. The notation will be like that. Okay. So here based on this orders, what we can understand is this is, I can say, the proper combination. This is going to be IK is 4 and P is of course 4 by 3. So number of rows in it is 4 and number of rows in it will be 4 here. So this is the proper combination. So G here is going to be IKP is going to be. Okay. And if at all P matrix is given such that, if P matrix is given as 3 by 4, in the order of 3 by 4, if P matrix is given as 3 by 4, then definitely G you have to consider as IK P transpose only. Okay, if at all P given as 3 by 4, then G matrix you have to take as IK P transpose you have to take. P transpose means will become 4 by 3. So 4 rows and 4 rows. So that's what you have to check with the order. Okay, what is the order given for P matrix? Okay, so based on that you have to proceed with. Okay, yes. So here this is actually going to be the correct combination, IKP. So now I can write G matrix here. If G is IKP P, then H matrix will be what? H matrix will be, in the second part P is there, a first part you can see P transpose, and in the first part identity matrix, in this the second part is identity matrix, that too that will be IM in H matrix, that is IM. IM is nothing but it is M is n minus k, this is 3, this is, and P transpose of course 3 by 4, this is of course, yeah. P transpose, what is P transpose? The first column become first row, so first column becomes first row, 1 1 1 0, this is, yes, 1 1 1 0, this is, second column becomes second row, 1 1 A1, this is 1 1 A1. Next, third column becomes third row, 1 0 1 B, this is 1 0 1 B. Okay, and I3, this is I3 means this is 1 0 0 0 1 0 and 0 0 1, this is, okay, this is H matrix. Okay, this is, yeah, this is P transpose and this is IM, H matrix. Then what will be H transpose matrix is our interest, yes, no, this is H transpose. So we need the transpose to this matrix. The first row becomes first column, 1 1, this is, so 1 1 1 0 1 0 0, next 1 1 A1 0 1 0, next third row becomes third column, 1 0 1 B 0 0 1, this is H transpose. So what is given? Code word. So what is a code word which is given as valid? 0 0 4 1 0, this is 0 0 4 1 0. Okay, now so for valid code word C into H transpose, you have to get 0 matrix, you have to get all zeros, you have to get. Okay, now if you multiply this C with H transpose, this C, okay, this is binary multiplication only, this C matrix you have to multiply with this H transpose matrix, you have to do multiplication. In this binary matrix multiplication, what the resultant you can expect is, if you do multiply this matrix with this matrix, what the resultant you will get is, the resultant will be sum of, okay, third, fourth, fifth, sixth rows of H transpose matrix. So sum of, this is third, the resultant you will get is sum of third, fourth, fifth and sixth rows of H transpose matrix. So if you multiply this C with H transpose, the resultant simply will be equal to sum of third, fourth, fifth, sixth rows of H transpose matrix. So by doing so, what you can expect is C into H transpose. What that elements you will get is, okay, so 1 plus 1 0, that is XOR addition you have to do. Now you can say A plus 1 plus 1 plus 1 will be what? 0 only. So it is A only you will get. This is A plus 0. So simply second element. The third element is, it is 1 plus 0 is 1 only. So B plus 1. Okay. So but C should be what I am expecting. C into H transpose should be, this is all zeros I am expecting. For valid code word, this is what I am expecting. Okay. This is the condition to be satisfied. So to satisfy this condition, so it is simply A only, the second element. So A is equal 0. And a B plus 1 should be 0. B plus 1 should be 0 means B is equal to 1. 1 XOR with 1 will be 0 only. And 1 XOR with 1 will be 0. So A is equal 0, B is equal to 1. A is equal 0, B equals to 1. So which option is correct is option B will be correct. This is option B will be correct. Okay. So I think we are already 8:30. So yes.
Yes, we will. So I will try to close with one or two questions. Okay. Yeah. So if you see this question here, this is. Yes. This is about cyclic redundancy check, CRC. This is. Okay. This question is about CRC. This CRC topic is newly added topic. This is added in the revised GATE syllabus. The last year only this topic is added in the GATE syllabus. Okay, CRC. So we'll do one question on the CRC. Yes. The CRC character for the message sequence, it is a message sequence given 100111101. Okay. CRC character for the message sequence 100111101 using divisor constant of 1001 is how much? Is what? Okay. CRC character we have to find out. Okay. The CRC cyclic redundancy check, it is very famously used in computer networks for error detection. This is very famously used in computer networks. Okay. Now, fine. So I don't want to give you that entire of analysis. I don't want to talk about that. How to proceed to this question is, the message sequence is, what is the message sequence given? 100111101. So whenever CRC is used for error detection, whatever the message sequence you are transmitting, okay, so for that message sequence, okay, first we have to append some zeros at the last. What, append some zeros. How many zeros to be appended? So what is the divisor constant given here? This divisor constant is also called as CRC generator. It got some other name also. Divisor constant is also called as CRC generator. Okay. So if the CRC generator having 4 bits in it, how many bits it is having? 4 bits. Then you have to append 3 zeros at the last. If it is having m bits, capital M bits, then m minus 1 zeros you have to append. You have 4 bits here, so you have to append 3 zeros here. 3 zeros you have to append. Okay. So to get CRC character, to get CRC, so CRC polynomial, to get that, this is the procedure we have to follow. Then whatever this modified message sequence, okay, you have to divide this modified message sequence with this divisor constant. That's it. Okay, so this is 1001111. So 1001101 Okay, just do division with this divisor constant, that is 1001. Okay, now, so this is 1. So you will get 1001. You will get here. Okay, and this is modulo 2 division only. This is the modulo 2 division means XOR addition you have to do here. XOR addition. If you do XOR addition, 1 plus 1 will be 0 only. 1 plus 1 will be 0. And whatever the remaining bits here, okay, you just bring them. Okay, bring down. This is 0, 0, 0. Now you have to discard this leading zeros. Okay, and you have to start with this leading 1 only. You have to start. You have to start with the leading 1 and 1. Again, and here no importance to this coefficient, okay, because this coefficient you will get all ones only, no importance to this, so that will be all ones only you will get. Next 1001 again, this is okay, and if you do that XOR addition, this is 1 plus 1 0 1 0 0 1 plus 1 0 and all zeros. This is, yes, no, this is 1 plus 1 0 1 1 plus 0, it is 1 0 0 and all zeros, and discard this leading 0. Okay, and start with the leading 1. Next 1001 1001. This is, yes, if you do that XOR addition here, what you will get here? 0 0 0 1 00. Then discard this leading zeros. Okay, start with the leading 1 here. 1 0 0 you have to start with. Now we can't do further division because the divisor constant is having 4 bits in it, the remainder having only 3 bits in it. The division we can't proceed further. Okay, so we have to stop here. And this remainder what you got here, this remainder,
So this remainder will become CRC for us. This remainder will be CRC. This CRC character, this is, or this is also called as a forward frame check sequence. It is also called as, the CRC character is also called as FCS, frame check sequence. That is 100. And one thing, if the divisor constant having 4 bits, okay, then the CRC character will have 3 bits in it. Okay, if the divisor constant having capital M bits in it, then CRC character will have M minus 1 bits in it. And one possibility is, if at all you got a situation like this, all zeros you got like this, okay, and 1 0, you got something like this, for example, okay, then if you discard all zeros here, then we left with 1 and 0, 1 0 we left with only 2 bits, but the CRC character must and should have 3 bits here. So in that case, what you have to do is, you have to, okay, in that case you have to discard this leading 3 zeros, then 0 1 0 will become CRC character for you. Okay, but here there is no such problem. Okay, so after discarding zeros itself, leading zeros, we left with 3 bits, and these 3 bits will become CRC character for us. Okay, and what they will do in CRC is some extra discussion here. This last zeros which we appended here, okay, and these 3 zeros will be they will replace with this CRC character. This zeros, okay, will be replaced with this CRC character, and that resultant code word will be transmitted. That resultant code word will be transmitted, and at the receiver side, whatever the code word they will receive, okay, that received code word they will divide again with the same divisor constant, and if at all they will get 0 remainder, then what it means is no error was occurred in transmission. And in the received code word, okay, after dividing the received code word with this divisor constant, if at all you will get non-zero remainder, then what it means is error was occurred in transmission. What it means is, so in that way the CRC is used for error detection. Okay, so I will close with this question. Okay, we'll do this question and I will close. Okay. So try to do this question. Yes. See, this is a random process here. This is xt is equals to u of t. Here u of t is a unit step function. Okay, u of t root e cos omega naught t plus theta, where e and omega naught are constants. Okay, and here theta is a random variable uniformly distributed in the interval 0 comma pi by 2. Okay, and the mean of xt is, what is the mean of this random process xt? So it's a good question. Okay, I'm expecting answers from you. I'm expecting good answer from you. What is the answer for this? Anyone? Okay, now see this. Here, this is the random process given. Here, u of t is unit step function, that's okay. And here, e and omega naught are constants. Okay, and here theta is the random variable which is uniformly distributed on the interval 0 comma pi by 2. So if you see the density function of theta here, f of theta with respect to theta, this is okay. So uniformly distributed means the density function is constant. So the density function is constant like this from 0 to pi by 2. Then what is the height will be? The height will be 2 by pi, because the area under density function should be equals to 1. Okay, length is pi by 2 means the height is 2 by pi. Okay, now fine. Now I have to find, yes, the mean of xt we have to find out. So expectation of xt, this is, so expectation of what is xt? This is ut root e, this is cos omega naught t plus theta, this is. So we have to find the mean for it. And how to find mean? Here theta is a continuous random variable, theta is a random variable, and this is of course continuous random variable, a range of values possible for it. And because it is a continuous random variable, it is integration, and for which quantity we are finding expectation, the same quantity you have to write. This is ut root e, this is cos omega naught t plus theta, and multiplied with the density function. What is the random variable here? Theta is the random variable. So this is f of theta d theta, where theta takes the values from 0 to pi by 2. This is. What are the values possible for theta 0 to pi by 2? Okay. Yes. Here f of theta is 2 by pi. So here integration is with respect to theta. Okay. Except theta, everything else will be constant for me. I can write outside to integration. Okay. So except theta, all other terms I can write outside. This is u of t root e, and f of theta is how much? 2 by pi. So this is, I'm writing 2 by pi outside, f of theta, and this is, we left with 0 to pi by 2 cos omega naught t plus theta d theta. Okay. Yes. So this will be u of t root e into 2 by pi. This is. What is integration of cos? The integration of cos will be sine omega naught t plus theta, and you have to divide with, what is the differentiation of this argument with respect to theta? 1 only. Okay, so integration of cos simply sine only you will get, and 0 to pi by 2 the limits will be. Okay, now it will be ut root e 2 by pi, and if you substitute the limits, sine omega naught t plus upper limit, in place of theta you have to substitute, upper limit is pi by 2 minus sine omega naught t, lower limit is 0. Okay. Now, so this is ut root e 2 by pi. Sine 90 plus theta will be cos theta only. This is cos omega naught t minus sine omega naught t. This is, so this is the mean what we got. Okay. So it is the expectation of xt, the random process xt. Okay. So 2 root e by pi, this is 2 root e by pi u of t cos omega naught t minus sine omega naught t. So option C will be correct here. This is, option C will be correct. Okay. So yes, option C is correct. Yeah, I will do. We done only one MSQ question only we done. So I will do another MSQ question, okay, multiple select type question. How that question is going to be? Because we done only one question, we'll do another question of MSQ and we will close this session. Okay. Yes. So this is MSQ type question. This is. So we'll close with this MSQ type question. Multiple select type question. MSQ. Here one or more options can be correct. Okay. So because this is a vast, it's very huge codes, communication systems. Okay. So many areas will be there. Okay. So if I have to talk about the important questions, means so many. Okay. So this will goes on like, okay, but we have to stop somewhere. Okay. So we'll close with this question here, with this MSQ type question. I will see how many of you can give answer for it. Okay. For a binary frequency shift keyed signal, this is, okay. So in examination they will clearly mention, they don't use the shortcuts FREQ like that, they will clearly write frequency, that's okay. So binary frequency shift keyed signal, it is BFSK, FSK this is, okay. This question is about FSK, okay. Okay, frequency shift keyed signal set. If the two signals are S1t, S2t, two signals are given. One is 100 cos 2 pi f1t. The another one is 100 cos 2 pi f2t plus 30. Okay, so the bit interval is given as TB. Both have the same interval, bit interval TB. The frequencies F1 and F2 are F1, F2 given 800 kilohertz and 600 kilohertz. F1, F2 is given. So here F1 means high frequency, you can understand. This is 800 kilohertz. You can denote with FH, high frequency. Low frequency here F2, this is 600 kilohertz. 600 kilohertz. Okay. For S1t and S2t to be orthogonal to each other, for these two FSK signals to be orthogonal to each other, the bit interval TB should be how much? The bit interval TB. Okay. So among the given options, what TB should be so that S1t and S2t will be orthogonal to each other? And this is MSQ type question, means one or more options can be correct here. Okay. Okay. Here the proper TB, okay, may not be only one option is going to be proper TB. Okay, maybe multiple options corresponding to proper TB can be here. Okay, and we have to check that. Yes, one thing here, if you observe the expressions for the FSK waveforms, here you can see some phase shift is there, some 30. If some phase shift is there like this, then this FSK corresponding to non-coherent FSK this is. If there is no phase shift here, then that FSK is called as coherent FSK. If some phase shift is there, okay, that can be 30, 60, what it may be. So this is corresponding to non-coherent FSK. Okay, for non-coherent FSK, condition for orthogonality is FH minus FL, in this case F1 minus F2 is equals to N by TB. This is the condition. Okay, this is the condition to be satisfied so that the given FSK waveforms will be orthogonal to each other. F1 minus F2 is N by TB. And for coherent FSK, what is the condition for orthogonality? FH minus FL is N by 2 TB. Okay, that is for coherent FSK, and this is the condition for orthogonality for non-coherent FSK, where N is an integer, means N can be 1, 2, 3, 4 like that. N can be any integer. Okay, now we have to find the TB value, we have to find out. TB is equals to N by F1 minus F2. Okay, F1 minus F2 is how much? 200k. 800k minus 600k will be 200k, this is. Okay, and all the options are given in microseconds. So I want to write this in microseconds. So this is n into this kilo 10 power 3. If it goes to numerator, this is 10 power minus 3, 200. Okay, now this is, so to write in micro, then what I will do is I will, this is yes, I will multiply with the 10 power 3 and I will multiply with 10 power minus 3. This is into 10 power minus 3. Okay, just to write in micro. Okay, this is 10 power minus 3 into 10 power minus 3. Then I just multiply with 10 power minus 3 and 10 power 3. Okay, fine. This is 200. So this is TB is equals to, okay. This is 10 power minus 6 means micro this is. So it is 1000. 1000 by 200, this is 5. 1000 by 200, this is 5n. This is microseconds. 10 power minus 6 means microseconds. So TB should be in this form, 5n microseconds, where n is an integer. N can be 1, n can be 2, n can be 3, like that. So if you see, so TB can be 5 microseconds you can go with. For FSK waveforms to be orthogonal to each other, 5 microseconds, or okay, n is equals to 10 microseconds, or if you take n equals 3, 15 microseconds. So many possible options here to choose TB value here, to make FSK waveforms to be orthogonal to each other. To choose TB, so many options we have, can be 5, can be 10, can be 15 microseconds, like that. Okay, but that should be integer multiples of 5, should be in the form of. So which options are correct here? This is, yeah, this is 5 microseconds, okay, and 15 microseconds. 2.5, 7.5, no possibility with these TB values, no possibility for FSK waveforms to be orthogonal. Okay, so B and D will be correct here. This is, okay, 5 microseconds and 15 microseconds. Yeah, okay, students. Yeah. So I'm closing the session now, and important topics for you will be, okay, I tried to cover some questions here, some important questions, okay, but so many will be there actually. As I said, this is a big course. Analog communication is there, digital communication is there, random variables, random process, information theory. It's a big one. It's a big course, and at the same time a good weightage you can expect in the examination. Definitely a good number of questions and good weightage you can expect. In the last year GATE examination, 18 marks came from communication systems. Out of 100, 18 marks came from communication systems. Okay, a good weightage you can expect. Okay, so I hope you prepared well already. Communication systems, you well prepared it. Okay, and as a last minute, you just go for this last minute revisions. Okay, because all exam is almost approaching. Okay, go for last minute revisions. Okay, and for classroom students, as I suggested, okay, for revision just do workbook questions, that's it. Okay, so you're doing workbook questions means what you can understand is the total subject is going to be revised. Okay, so do workbook questions. Okay, and I hope you already written the test series, and if not, try to write that FST test series and mock test. So go for those test series. Okay, then you will definitely come to know the environment, means how to manage the time, how the time management, you will come to know how to manage the time, okay, by writing the test series. I hope you will do that. Okay, and the important areas for examination, communication systems, important areas will be, as you know, the digital communication is much important compared to analog communication. So but you can't ignore analog communication completely. Okay, the questions you can expect from analog communication also, but you can easily attempt them. Okay, but digital communication you have to concentrate. Okay, like the topics of random process, information theory, and finding probability error. Okay, for digital modulation schemes. Okay, so concentrate on those topics. Okay, concentrate much on those topics, because definitely, okay, good amount of questions you can expect from these topics. Okay, yeah, thank you students, and thanks for your time, and I wish you very much a good success and good luck for the coming examinations. So all the best to you, and God bless you guys. Thank you.